Now we want to talk about integrals that involve secant and tangent, so combinations of those things. So just like we did with sine and cosine, we're going to use the Pythagorean identity that involves secant and tangent. And with sine and cosine, remember the first two guidelines basically put you in a situation where you could set up a u substitution, and that's exactly what's going to happen here. So the first thing we want to check for when we're looking at these integrals is if the power of secant is even and positive. So when secant is even, right, we can always pull out a secant squared. And if you pull out secant squared, well, that's going to become your du. And then we'll use the Pythagorean identity to turn all the remaining tangents into secants. So if you look right here, you can see the secant squared we pull out, right? That's going to be our du, right? And so the idea here is when we set up these integrals, we want to be able to u substitute where u is tangent x and du is secant squared x dx. So by simply pulling out one secant squared and putting it to the end, you'll still have a combination of even secants that we can use this Pythagorean substitution. Then we can expand this and now do this doing a u substitution. Conversely, if tangent is odd, right, then if we pull one of them away, we're left with an even number of tangents. So what we do is we borrow a tangent, right, and we take one of the secants away. So we pull out a secant tangent. Secant tangent is the derivative of secant. So now what we'll do is we'll convert the remaining secants into, or the remaining tangents, excuse me, because we'll have an even number of them. We can convert those into secants, expand, and now we can let u be secant x, and our du will become secant tangent x dx, right? If neither one of these two scenarios is feasible, right? So let's say we have no secant factors at all. It's just some combination of tangents. Well, then what we do is we pull one tangent squared out and we convert that tangent squared into secant squared minus 1. Then we expand and we see if we can break this integral up into a combination of things that may allow us to go back to guidelines 1 and 2. And you repeat this if necessary. So you'll pull out a secant tangent squared, convert it to secant squared minus 1, distribute everything out, evaluate the two integrals that you have left, and then we can, oh, sorry, this k should not be here, right? Because you're only going to pull out one of them. And so we'll then simplify this out, see if we can apply guidelines 1 and 2, and then we may have to repeat some of these with that format. If the integral is the form of just secant, right, and secant is odd and positive, well, then we can do integration by parts. And we actually looked at this in the integration by parts section when we did the example of secant cubed, right? However, if guidelines 1 through 4 do not apply, try converting any remaining secants, try converting everything into sines and cosines, and then simplify and use the guidelines for our sine cosine integrals. So let's look at some examples of how to apply this. So notice here that secant is odd, or excuse me, tangent is odd, right? So what this tells us we should do is look guideline 2, and we should pull out a tangent, right, and a secant, and then try to do a u substitution. However, this one's interesting because we have a secant to the 1/2 in the denominator. So I don't actually have any secants in the numerator that I can pull out, but we can actually get around that. So the first thing I'll do is I'm going to remove one of these tangents. So that leaves me with tangent squared x. And I'm going to leave the square root of secant alone in the denominator. Then what I want to do, right, is I pulled out one of my tangents, but what I really need is a secant tangent dx for my du. Well, I'm actually allowed to put the secant here as long as I also do it to the denominator. So I'm really going to multiply this integral by secant x over secant x. So now I have my du, and now I can convert these remaining tangents into secants, and we can simplify the integral. So my integral now, right, I'm going to take tangent squared, and I'm going to replace it with secant squared minus 1, right? I have in the denominator now a square root of secant x, so that's secant to the 1/2 times secant to the 1. So in the denominator, what I have is now secant to the 3/2 x. I'm going to leave my secant x, tangent x, and now I'm ready to do a u substitution. So we're going to let u be secant of x. Our du is secant tangent x dx. So now when I translate this integral into variable u, I have u squared minus 1 over u to the 3/2 du. Now before we integrate this, we can actually simplify this down. So since the denominator just has one term, this is actually u squared over u to the 3/2 and 1 over u to the 3/2. So I can simplify that and say, well, this is really u to the 1/2 minus u to the negative 3/2 du. So now I can integrate using a very straightforward power rule. So I'll get 2/3 u to the 3/2 minus u to the negative 1/2, and when I divide by negative 1/2, this turns into positive 2. Now that I'm done, I just put back in what u stood for. So I get 2/3 secant to the 3/2 x plus 2 secant to the negative 1/2 x plus c. Right? So let's look at another one. This one, right, notice inside of their two functions that they're both 3x. So this is very important. You can apply these rules to any combination of secant and tangent as long as the stuff inside the trig functions are the same, okay? So once again, we have an odd number of tangents, but we have an even number of secants. So since secant is even, this is guideline 1. So it says we'll pull out a secant squared and save it for your du. So if I remove one secant squared, I'm left with secant squared 3x, tangent cubed 3x, and then here's my secant squared 3x, and this is going to become our du. So then I need to convert the remaining secants into tangents. So when I do that, I'll have 1 plus tangent squared 3x times tangent cubed 3x times our secant squared 3x dx. So now I'm ready to do a u substitution where u is going to be tangent of 3x, but this is where the 3 is going to come into play. When I take my du, I have to do the chain rule, and so I'm actually going to have 3 secant squared 3x dx. So notice in here that I don't really have that extra 3. So by simply dividing both sides of this equation by 3, when I translate this into variable u, I'm going to replace secant squared 3x dx with du over 3. So I'm going to pull the 1/3 out front, and I've got the integral of 1 plus u squared times u cubed du. So I'm going to distribute that before I integrate so I can do a power rule, and I've really got u cubed plus u to the 5th du. So when we anti-differentiate, we'll get 1/3 u cubed over 3 plus u to the 6th over 6 plus c. And now when I come back in and replace my tangent, I'm going to go ahead and distribute this 1/3. So I'm going to get tangent cubed 3x over 9, because 3 times 3 is 9, plus tangent to the 6th 3x over 18. Oh, I did this wrong, guys. Sorry. This should be u to the 4th over 4. So this is actually going to be a 12, right? I forgot to up my power when I did this, so be careful. So 3 times 4 is 12, and then this is 18, right, plus c. Right, this one is just powers of tangent. So what it told us to do, right, was it said just pull out one tangent squared. So if I pull out a tangent squared, I'm going to get tangent squared x, right, times tangent squared x dx. Then it says take the tangent squared you pulled out and try to turn them into secants and see if that helps solve the integral. So we'll do that by replacing that second tangent squared with secant squared x minus 1. So now let's simplify this integral and see if this gets us anywhere. So now I have the integral of tangent squared x secant squared x dx. We'll go ahead and do this, right? Minus the integral of tangent squared x dx. So this first one, right, I have a secant squared, that's a derivative, and I have everything else in terms of tangents, so I can actually integrate this using a u substitution. This one, however, I can't integrate tangent squared directly, so we're going to make the substitution again. So let's do that one more time. So now what I have, right, is the integral of tangent squared x secant squared x dx. And now I'm going to replace this with secant squared minus 1 again. Well, this I can integrate directly because that's the derivative of tangent, and we can always integrate 1. It's just going to be x. So for the first integral, however, right, we're going to need a u substitution. So if we let u be tangent x, then our du here is secant squared x dx. So this is really just the integral of u squared du. And then, right, I've still got my integral of secant squared x minus 1 dx. So when I integrate this, the first one is going to be u cubed over 3. Then my second integral, right, the antiderivative of secant squared is just tangent x, and this negative is going to get distributed, so this is actually going to become plus x plus c. So my final answer, I'm just going to replace u with what u stood for. So I'll get tangent cubed x over 3 minus tangent x plus c. All right, so let's look at one more example. So this doesn't really fit any of our guidelines, right? So the first guideline said if the power of secant is even and positive. Well, our power of secant is 1, so it's odd. So we can't do guideline 1. Guideline 2 says, well, if the power of tangent is odd and positive. Well, tangent's even, and it's actually negative because it's in the denominator. If there are no secant factors, that was guideline 3, well, we do have a secant factor. The fourth guideline says, well, if there are no tangent factors, well, that's not true either. So this is going to work out to be guideline 5, which just says rewrite the integral in terms of sine and cosine and see if we can solve it from there. So we're going to rewrite this. Secant is 1 over cosine. So secant is going to become 1 over cosine x. Tangent is sine over cosine, but it's in the denominator. So instead of doing sine over cosine, because it's in the denominator, we actually multiply times the reciprocal. So I actually get cosine squared x over sine squared dx. So now I can simplify this down. So I can cancel a cosine out of the denominator with one of my cosines in the numerator. And now I need to integrate cosine x over sine squared x dx. So this is actually a u substitution problem. If we let u be sine of x, well then our du is cosine x dx. So I have my du right here, I have my u right here, so this integral simply becomes 1 over u squared du. If you want to rewrite it before you integrate to u to the negative 2, right, now we can just do a straight up power rule. So we'll get u to the negative 1 divided by negative 1 plus c. So this is just going to be negative 1 over sine of x plus c. So this is perfectly acceptable, but if you, for some reason, just want to write this without having sine x in the denominator, remember 1 over sine x is cosecant x. So these are actually equivalent answers. So they're both correct for this integral, but I would be okay if you stop there. All right, so the only thing we didn't really talk about with sine and cosine are going to be how to deal with integrals where the stuff inside the functions are different, right? And I'm not really going to test you on this, but the reason I want you to see it is because if you have to go on and take differential equations or maybe do some advanced calculus, you will come into contact with this type of thing and you need to know how to separate them out. So what we've done here is these are all reworkings of the sum difference formula, right? So how to do cosine of a plus b or sine of a plus b. So by reworking these, you have all your possible combinations, right? You could have two sines, you could have a sine and cosine mix, or you could have two cosines. So it's really easy to see how to do this when we look at an actual example. So what I have here is sine of x times cosine of x. So what this is saying is our m is 5, right? And our n is 4. So if you look up here on this table, here is how to work with a sine cosine mix. So we can take sine of 5x, cosine of 4x, and we can rewrite it using this trig identity. So the 1/2 is multiplied by everything. And the first term says we'll take sine of m minus n. So m minus n here is just going to be 1. So I'll have sine of x. And then we're going to add that to sine of m plus n. So that's sine of 9x. Now, integrating this is the same as integrating this. So I'm going to move the 1/2 out front, and now we just have to compute the integral of sine of x plus sine of 9x dx. So this is easily anti-differentiated. The antiderivative of sine is negative cosine, and the antiderivative of sine 9x is negative cosine of 9x, and then I have to divide by 9. And so you can always check yourself, right, by taking the derivative of this, and you should end up right back here. Right, so the next thing we need to make sure we understand how to do is how to do trig substitution. So in the review day video for review day part 2, I actually went through and in detail derived and explained where these setups come from. But basically any integral where you encounter u squared, a squared minus u squared, a squared plus u squared, or u squared minus a squared, we can do trig substitution. So basically what we're doing here is we're translating all the integrals into variable theta. So it's sort of like doing a u substitution, but it's a little bit more advanced. And we're going to translate the integral into variable theta, integrate the trig functions, which actually, believe it or not, will make your life easier, not harder. So like I said, revisit the review videos. I put all of the concept notes on here for you, but I actually explain where these come from and how to set up these triangles when we're doing problems. So the first example I want to look at is dx over x squared times the square root of 9 minus x squared. So this is actually, right, this radical, and the radical is always going to lead the discussion here, right? So you want to look at the form of the radical. So this radical is of the form a squared minus u squared, right, where your a is 3, right, and your u is just x. So what we want to look at, right, let's set up our triangle. And theta, right, is always the bottom left corner. This is a minus case, so this is actually the hypotenuse. So 3 goes here. The radical itself goes on the base, and the height of our triangle is x. So in order to set this up, I need to translate this guy into variable theta. So the first thing I do is I'm going to state what x is. So remember, you look at the triangle and you look at the two sides that don't have the radical in them. So this is opposite over hypotenuse. So x is 3 sine theta. Then, right, this guy is a dx, so we need to calculate dx. Dx is 3 cosine theta. And then the radical itself will end up being 3 cosine theta. So if you look at the triangle, you can see that that's true because this is adjacent over hypotenuse. So now I want to translate this integral into theta by using these 3 elements. So the dx in the numerator is 3 cosine theta. Oops, and don't forget your d theta. D theta. The denominator, we have an x squared. So that means I need to square this expression. So I'll actually plug in 9 sine squared x. The radical itself will be defined as 3 cosine theta. So then we simplify and then integrate. Well, the 3 cosine theta cancels the 3 cosine theta. And what I'm left with is 1 over 9 sine squared x, oops, sine squared theta, don't know why I did that, d theta. And even though this looks like you might be stuck, we actually know what 1 over sine squared is. So this is 1/9 times the integral of cosecant squared d theta. Well, cosecant squared, just like secant squared, is actually a known derivative. So the antiderivative of cosecant squared is cotangent squared. More specifically, it's negative cotangent squared. So I'll get negative cotangent squared over 9 plus c. So we're not done because you're not allowed to leave the integral the answer in terms of theta because the integral asked you to integrate with respect to x. So what we do at the end of the problem is we just translate back. So if you look at the triangle here, well, cotangent is 1 over tangent, and tangent is opposite over adjacent. So cotangent is adjacent over opposite. So also keep in mind that this is cotangent squared. So that means we have to square each one of these sides. So if you square the radical, right, you just get 9 minus x squared. If you square the opposite side, we get x squared plus c. Oops, I messed up. Sorry guys, my bad, I caught my mistake. The antiderivative of secant, is just cotangent, not cotangent squared. My mistake, sorry. So this is negative cotangent theta over 9 plus c. So this is easier because we don't have to square these sides. So it's still adjacent over opposite. So we say negative square root of 9 minus x squared over x, but it's multiplied by 9 in the denominator, so we get 9x plus c. So this is actually the correct answer. All right, let's look at another one. So the radical in this case is the plus case, right? And that's what happens when you solve for the hypotenuse of a right triangle. So this guy is of the form u squared plus a squared. Remember, a is always the constant, not the expression. So our a here is 1, and our u is 2x, because see, this is 4x squared, so the square root of that would be 2x. So if we set up our triangle for this problem, theta is always here. The radical is the hypotenuse in this case. So the base is a, and the height is u. So now when I set this up, what's going to happen is we can't just say let x equals, it's 2x, because the side without the radical are the opposite in the adjacent side. So that means tangent of theta is 2x over 1. So 2x equals tangent theta. But I need to know what x is, so I need to solve this for x. So I get 1/2 tangent theta. Then we calculate dx. That's 1/2 secant squared theta d theta. And the radical, 4x squared plus 1, is going to just be secant theta, because the radical here, right, is in the hypotenuse, and so what we have here is adjacent over hypotenuse is cosine, but we want to solve for the radical, so we want hypotenuse over adjacent. So now I'm ready to translate this. So dx is 1/2 secant squared theta d theta. The denominator is just secant theta, so I can actually cancel one of these secant thetas. So now I just want to integrate 1/2 secant theta d theta. So the antiderivative of secant and cosecant are actually known. Remember that secant is 1 over cosine. So whenever you integrate something that's like 1 over u, it involves a natural log. So the antiderivative of this is the natural log of secant theta plus tan theta. Now the way I remember this is, well, the derivative of secant is secant tangent, so the antiderivative of secant is ln secant plus tangent. If you had cosecant, you would get a very similar result. You would have negative 1/2, and you would say ln of cosecant plus cotangent, because the derivative of cosecant is cosecant times cotangent. So then, just like before, we have to go back to variable x. And secant is actually right here. It's the actual radical itself. We could also have gotten it off the triangle. We would have said opposite, or hypotenuse over opposite. So I'm going to replace secant with the square root of 4x squared plus 1. To do tangent, I could have grabbed it right here. It's 2x. Or I could have looked at my triangle. Tangent is opposite over adjacent. So we get plus 2x plus c. The absolute value bars are necessary because remember, you can't have anything negative inside a natural log. So we need to make sure that whatever x values we're saying are allowed in here, that the resulting expression works out to be positive. All right, let's look at another one. So in this problem, we don't actually see the radical, but that's because, right, it's raised to the 1/2. So remember, any kind of fractional exponent where the denominator is a 2, that's actually a radical. So what this integral is actually saying is that this is dx over the square root of x squared plus 1. So there's your x squared plus 1 to the 1/2, and then we cube it, okay? So when we're dealing with a radical of the form, right, u squared plus a squared, once again, that's the hypotenuse of our triangle. So if we set up our triangle, the radical goes here. Our a is 1, so the adjacent side is 1, and the opposite side is just going to be x. So that means that x is 1 tan theta, dx is secant squared theta d theta, and the radical is just going to be a, which is 1, secant theta. There's no d theta needed this time. So if we translate this integral, our dx is secant squared theta d theta. The radical is secant theta, but notice here it gets cubed. So in the denominator, I'm going to have secant cubed theta. So this cancels the secant squared out of the top. We're left with 1 secant in the denominator. So we know how to anti-differentiate secant. I just showed you in the last problem, right? But this is 1 over secant. So we can write all trig functions, right, have reciprocal identities. And 1 over secant is simply cosine theta. So the antiderivative of cosine is sine. And if we go back to the triangle, right, notice we don't have any signs defined over here, but that's easy, right? The triangle lets us grab any trig function we want. So sine is opposite over hypotenuse. So this works out to be x over the square root of x plus 1 plus c. So even though there's a little algebra involved in these problems, if you notice, none of these integrals were solvable on their own. You couldn't do u substitution. You didn't have all the elements. But by translating it into variable theta, even though there was a little bit of algebra involved, everything simplified down to a nice clean integral that we could easily anti-differentiate. All right. The next topic we need to cover is partial fractions. So once again, if you revisit that review video for part 2, I actually went very in depth on partial fractions and kind of explained why things are the way they are. So please watch that. I kind of gave a little mini lecture on it. What I'd like to do now is just focus on the problem solving aspect of these problems. So once again, I wrote some guidelines for you. So many of you may not remember what an improper fraction is. So an improper fraction is any fraction where the numerator is bigger than the denominator. So if you encounter a fraction where you have polynomials over polynomials, right? If the power of x in the numerator is bigger than the power of x in the denominator, it means the numerator is bigger than the denominator. And so we need to simplify improper fractions, and we can do that by actually doing log division. What you'll get is a polynomial plus another fraction. The polynomial will always be able to be integrated directly, but then once we deal with this fraction, this is what we'll need to split up into partial fractions. So you want to kind of think of these problems as a situation where this fraction you're integrating was the sum of multiple fractions that somebody's already combined, added up, found common denominator, and simplified. So what we're actually going to do is undo that algebra, which seems a little cumbersome at the beginning, but it makes the integration a lot easier. So the first thing you're going to do is factor the denominator completely as far as you can, and you'll be left with linear terms and maybe some quadratic terms, but those quadratics you have to verify that they're irreducible, meaning they don't factor anymore, right? Any linear factors, we put constants over the lines. Any quadratic factors, we put lines over quadratics, and that's because the derivative of a line is a constant and the derivative of a quadratic is a line. The exponent with the factor, so if you have a line raised to the m, that means you need m fractions to account for that factor. If you have a quadratic that's irreducible raised to the n, then that means you will have to set up n partial fractions to account for that. So if you have repeated factors, is what we call that, you need multiple individual fractions to deal with that. So before we get into integrating, let's just look at how to break something simple up into partial fractions. So the first thing I have to do is factor the denominator. And this denominator factors into x minus 2 times x minus 3. So I only have two linear terms here. So this means that this fraction was most likely the sum of a fraction with an x minus 2 denominator and a second fraction with an x minus 3 denominator. Notice that the powers here were 1, so that means I only have to devote one fraction to each of those terms. Now what you're supposed to do is we have to do some algebra to solve for a and b. So what we do is we want to eliminate all the fractions. And we eliminate all the fractions by multiplying the entire equation by their common denominator. You'll always know what the common denominator is because it's the original denominator you started with. So we want to multiply this by x minus 2 times x minus 3. So this has to be done across the whole expression. So over here, it's going to completely cancel, and you're just left with 1. For this fraction, the x minus 2 will cancel, so a is only multiplied by x minus 3. For b, x minus 3 cancels, so you're only dealing with x minus 2. So now we have to solve for a and b, and since we have two unknowns, we need two equations, and the way we generate those equations is by plugging in values of x. So theoretically, you can pick any x value you want because this expression should be true for any x, right? But we can actually be strategic about this. So for every linear factor, what you want to do is you want to pick a value of x that would turn that factor into 0. So here, if you were to plug 3 in, it would zero out this factor. And here, if you plug 2 in, it would zero out this factor. So let's try using those values. So when x equals 3, the left side of the equation is 1 all the time, right? But if I plug in 3 here, this is 0, so all I'm left with is this part of the expression. So I have b times 3 minus 2, which is 1, so b just equals 1. If we plug in x equals 2, the left side is still 1. But now this term gets zeroed out, and I just have to deal over here. So this is going to be a times negative 1. So a equals negative 1. So that means that 1 over x minus 2 times x minus 3, and you got to be careful to make sure you throw these constants in the right spots here. This is going to be negative 1 over x minus 2 plus positive 1 over x minus 3. So if you actually found a common denominator over here, simplified this fraction down and added it up, it would simplify back into the original thing you started with. All right, let's do one that's a little more complex. Let's look at something like this, okay? So the first thing I have to do here is I have to factor this denominator completely. So I'm just going to kind of do this off to the side. So I'm just going to write the denominator down. All right? And the first thing I notice is that every one of these terms has an x. So I'm just going to pull the x out front. And notice I have a quadratic here. So now I need to check, does this quadratic factor? And it actually does. It factors into x plus 1 squared. And so if we FOIL this out, we do in fact get this. So this is now what my denominator simplifies into. So my fraction that I'm working with, right, is 5x squared plus 20x plus 6 divided by x times x plus 1 squared. So these are both linear terms. I need one fraction devoted to this, and I'm actually going to have two fractions devoted to this. So even though this FOILs out into a quadratic, it's a linear factor. So we put constants, right, over lines. So I'm going to have a over x. That takes care of this guy. And remember, the way we deal with repeated roots is the following. You do b over x plus 1, and then you'll have a second term that's x plus 1 squared. If this had been x plus 1 cubed, I would have had a third fraction that was d over x plus 1 cubed. So you're not allowed to skip any exponents. Now it's okay if some of these numbers work out to be 0 when we calculate them, but you have to basically, with partial fractions, create the maximum number of partial fractions that could have been condensed down to create this guy. So just like before, we're going to eliminate our fractions by multiplying by the common denominator. So the common denominator here goes away, and I'm just left with the numerator. Here, the x is canceled, so a is multiplied by x plus 1 squared. B gets x and one of the x plus 1s, and C is only left with x. So the values here that are going to make this these terms zero out are going to be 0 and negative 1. So let's deal with 0 first. So when x equals 0, the left side of this equation is just 6. But when I plug in x equals 0 over here, notice this gets zeroed out, this gets zeroed out, so all I'm left with is a times 1 squared, which is just 1, so 6 equals a. So that one was pretty straightforward. When x equals negative 1, the left side of our equation is negative 9. But if you look over here, any term with an x plus 1 turns into 0, so I'm just left with c times negative 1, which is negative c, so that means c is 9. So now I'm out of linear terms, right? And or I'm out of convenient values of x. So now I have to pick a third value of x to solve for the third variable, because we still don't know what b is. So the most obvious choice would be to pick 1, because zeros and ones are really easy to work with. We've already used 0, we've already used negative 1, so let's pick x equals positive 1. So if x equals positive 1, when you plug in 1 on the left side of the equation, we get 31. When we plug 1 in here, right, 1 plus 1 is 2, so when you square that you get 4, so I'm going to get 4 times a. Over here, b times 1 is 1, but then I have to multiply it times 2, so I get 2b plus c. Well, since I know a is 6, right, and I know c is 9, now I can say that 31 equals 4 times 6, which is 24, plus 2b plus 9. And when we solve for b, we get b is negative 1. So now if I want to integrate, my integral is now 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared. This can all be integrated pretty much directly. So we know the antiderivative of 1 over x. The antiderivative of 1 over x plus 1 is easy because this dx is just 1. And here we can actually do a u substitution where u is 1x plus 1. Our du is still 1. So you're really just integrating 1 over u squared. So when we do this, we get 6 times the natural log of x minus the natural log of x plus 1 minus 9 over x plus 1. And that's because u to the negative 2 becomes u to the negative 1, which puts it back in the denominator, divided by negative 1, which made this a minus sign, and then we have plus c. So for these linear terms, a lot of times you're just going to end up getting lots of natural logs because the idea is to have 1 over u, 1 over u, 1 over u. All right, let's look at one that's a little bit more complex. Right, so this one has a little bit more algebra steps, and so you're going to have to make sure you write kind of small on this one because I accidentally didn't leave quite enough space for this. But just like before, let's factor this denominator down. Okay, so I'm going to just draw a little line up here so I can use a little space up here. Right, so this denominator, x squared minus x times x squared plus 4. Well, the x squared plus 4 cannot be reduced any further, but I can factor an x out of the first term. So I get x times x minus 1 times x squared plus 4. Now this thing is completely factored, but notice I now have a quadratic term I have to deal with. So if we break this up into partial fractions, we're going to get that 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4. Well, this is a linear term, so we'll have a over x. This is a linear term, so we'll have b over x minus 1. But this is a quadratic, so we put a line on top of a quadratic. So now I have 4 variables to solve for, right? But just like before, I can use the fact that these are linear terms to get some really convenient values of x to help cut down on the algebra. So the first thing we're going to do, just like in all the other problems, is we're going to multiply by the common denominator. And now we simply have to solve the equation 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus, and be careful about this, you have to put cx plus d in parentheses times x minus 1. So just like before, let's deal with the linear terms first. This will make things quite nice for us. So when x equals 0, the left side of this equation just becomes negative 8. On the right side of the equation, this term goes away and this term goes away, so I only have to plug 0 in here. So we'll get a times negative 1 times 4. So this is really negative 4a equals negative 8. So when you divide both sides by negative 4, you're going to get that a equals 2. The other linear term says, well, let's try x equals 1. So when you plug in 1 on the left side of the equation, you're going to get 2 minus 4 is negative 2, minus 8 is negative 10. Make sure I did this right. 2 minus 4 is negative 2. Negative 2 minus 8 is negative 10. On the right side, any term with an x minus 1 disappears. So we only have to plug in 1 right here. So we'll get b times 1 times 5. And so this is negative 10 divided by 5. So this says that b is equal to negative 2. So we got 2 of our constants down, right? But now we have to pick 2 more values of x to find c and d. So when we do this, right, we've used 1, we've used 0. So let's pick negative 1, because 1s and 0s are pretty easy to work with. So when x is negative 1, the left side of the equation becomes negative 6. The right side of the equation, what I'm going to do is I'm going to go ahead and plug in my a and b as I go to simplify my algebra. So my a was 2, right, times negative 2, because negative 1 minus 1 is negative 2. When you plug negative 1 in here, it becomes positive 1 plus 4 is 5. So once you've kind of thrown these numbers in here, you're going to see they're going to repeat later. So it kind of makes it easier when you're doing the algebra. B was negative 2, so this is minus 2 times negative 1 times 5 plus c times negative 1 is negative c, right, plus d times negative 1 times negative 2. So this simplifies into the equation 2 equals negative c plus d, right? So for lack of a better option, let's just try x equals 2. You can technically try any value of x that you want. So we're going to do this again. When you plug in 2, the left side of the equation becomes 0. And then we have 2 times 1 times 8 minus 2 times 8 plus 2c plus d times 2 times 1. So this simplifies into the equation 8 equals 2c plus d. So in order to find c and d, I just need to solve this system of equations. So an easy way to do that is using what's called the elimination method. So if you look at the c's, right, we have a negative c and a positive c. So if I actually multiply this whole equation by 2, well then this will become negative 2c and positive 2c, and those will actually cancel out. So what we want to do is we want to multiply this first equation by 2 all the way across, and you'll actually get 4 equals negative 2c plus 2d. This is just algebra you guys should learn back in high school. And what we're allowed to do is we're allowed to add these equations together. So 4 plus 8 is 12. The 2c's cancel, and we get 3d. So d is 4. Then you can come back to either of these two original equations and plug in d. Well, I would pick the first one. It just looks a little simpler. So 2 equals negative c plus 4. So we can see that c is going to equal 2. So you add c to both sides, subtract 2 from both sides, and now we're ready to go. So we want to integrate 2 over x minus 2 over x minus 1 plus 2x over x squared plus 4. Excuse me, it's 2x plus 4, right? Because it was c, x plus d over x squared plus 4 dx. So then you just want to scan across and see, am I ready to integrate yet? So this is easy to integrate. This is easy to integrate. We have a bit of a problem here. If you try to use a u substitution, right, well then you need a 2x. We have a 2x, but we have this extra 4. So what we really want to do is we want to split this up into 2 fractions. So now we'll say we have 2x minus 2 over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4 dx. So now this can be integrated directly. This can be integrated directly. Now I have everything to u sub this one, and this is actually a form of arctan. So the answer to this is 2 natural log of x minus 2 natural log of x minus 1. This can be done with a u substitution, so you're going to get actually 1 over u when you do this integral. So this just becomes the natural log of x squared plus 4. And this is actually a arctan, right? And so it's 4 times, right, arctan of a over 2. So I'm just going to write down this integral in case you don't remember this. The integral of 1 over x squared plus a squared dx is 1 over a arctan of x over a plus c. So in our problem, our a is 2, but I also have the 4 out front, so I'm going to get 4 over 2, which is just 2 arctan of x over a. So a is 2 because a is squared plus c. Okay. So there's one more method I want to show you, and that's how to deal with repeated quadratic factors. So with repeated quadratic factors, right, what we have here is an irreducible quadratic that's raised to the 2. So when you set this up, right, your fraction is 8x cubed plus 13x over x squared plus 1 squared. So I have to have 2 fractions devoted to this, but they're quadratics, so I have to put a line. Oops, this should be a b over x squared plus 1, and then I deal with the repeated fraction x squared plus 1 squared. So we don't really have any convenient linear terms to zero things out for us. So there's another method you can use algebraically to try to solve for these 4 constants. We still start by multiplying everything by the common denominator. Okay, so that's going to wipe out the denominator over here. And now we got to be careful because of these lines. So we're going to have quantity ax plus b times x squared plus 1. So you got to have parentheses, right? It's not going to multiply right. But then over here, the whole denominator goes away. So what we've got here is basically a polynomial equals a polynomial, but we need to actually turn this into a polynomial form. So the first thing I'm going to do is I'm going to FOIL these first 2 terms. So we're going to get ax cubed, right, plus bx squared plus ax plus b. And then what we want to do is we want to group things by powers of x. So I only have 1 cubed term, so we'll just leave ax cubed alone. I also only have 1 squared term, so we're going to leave bx squared alone. But notice I have 2 things attached to an x. So what we do is we factor out the x, and we write this as a plus c times x. And then I have 2 terms with no x at all. So just to be consistent, I'm only going to put these in parentheses so we can see that this is in fact a polynomial. We have our cubed term, our squared term, our linear term, which is 1, and we have this as our x to the 0 term. So then I'm going to set this equal right to the left side. So when you have a polynomial equaling a polynomial, what that means is their respective coefficients must equal each other. So we'll start with the highest power of x. We have our cubics. So over here I have an 8x cubed and an ax cubed. So that means this term and this term have to be equivalent, so I can set their coefficients equal to each other. So a is 8, right? Notice for the x squared, I have an x squared on the right, I have bx squared, but I don't have an x squared over here. And that's because the x squared term had a coefficient of 0. So remember, that's what we do in polynomials. If there's no x squared term, it's really just 0, so we don't write it. So that means 0 equals b. If we look at the x term, well, we have a plus c times x equals 13x. So that means a plus c is equal to 13. Well, since I already know 8 is a, that means 8 plus c is 13, so c is 5. And then for the last term, right, I have b plus d, right, times x to the 0. But over here, right, I don't have a x to the 0 term. So that means that coefficient was also 0. So that means 0 equals b plus d. But I've already figured out that b is 0. So that means d is 0 as well. So that's actually a really cool way to do it. If you just do a little algebra and simplification up front, you can find all of your equations very, very quickly. So now let's go back and actually integrate this. So we need to fill in all the holes, right, up here for our partial fractions. So what we want to integrate is ax plus b, so that is 8x, right, b was 0, over x squared plus 1, plus 5x plus 0 over x squared plus 1 squared dx. So what we can do now, the first one can be done straight up with a u substitution. So this will become our u. Our du is 2x. So what I can do here is take 2x out of here. So this is really 4 times 2x. So by simply doing a u substitution, this first term just becomes 4 times the natural log of x squared plus 1. For the second one, I can also do a u substitution, where u is x squared plus 1, du is 2x. So I simply plug in du over 3 and simplify. And so when you do your u substitution for this, you'll get 3 over 2 x squared plus 1 squared plus c. So I definitely recommend, sorry, this was supposed to be a dx. I definitely recommend for this part, for practice, right, you setting this up where u is x squared plus 1, du is 2x dx. So I definitely recommend you trying to work this out in detail on your own, but you should get 3/2 times 1 over x squared plus 1 quantity squared. So just like I mentioned in review day on impartial fractions, you can see because of the algebra, they can get really cumbersome. So if I want you to work something out to completion, it will be something really straightforward like the first example we worked, where everything breaks down into just 1 or 2 factors or a lot of linear terms. But one thing, if you look at my old exam that I did do this semester, was I had people set up the components without actually solving. So you do need to make sure you understand the rules and when to put a constant on top, when to repeat the fraction, when to put a line on top. So I may, on the final exam, ask you to set up a partial fractions problem, but just maybe not solve it all the way to the end. Or if I do want you to solve, it'll be something with very basic, simple algebra. So you're not, you can see from those examples, you can't just do a ton of them. All right, so the last topic we have to talk about are improper integrals. And we actually saw a little bit of this in Unit 3 when we did the integral test. These are very, very important integrals. If any of you go on to take any statistics courses, you'll see an improper integral there. You may see them in some physics courses, but there is an actual need of why we would integrate to infinity, or why we would integrate around a discontinuity. So I put on here the way we set this up, right? If you have an indefinite integration limit, means there's actually an infinity involved. If it's the upper bound, what we do is we replace infinity with the letter b, because we usually integrate from a to b. Then we take the limit of the result as b goes to infinity. So you really need to think about this like this, okay? So what we're going to do is we're going to complete the integral, and then when we finish the integral, we then take the limit. If the lower bound is negative infinity, then we usually replace that with an a. So we're integrating from a to b. And then we take the limit as a approaches negative infinity. So just like before, you're going to figure out the limit, or figure out the integral, excuse me, then do the limit onto the result. We can also integrate across